In an AC circuit containing only a resistor, we connect a resistor to an alternating current or AC supply. The voltage from the AC source is given by the equation V equals Vm sin omega t, where Vm is the maximum voltage and omega t represents the angular frequency over time. According to Ohm's law, the current in the circuit is equal to the voltage divided by the resistance. So if we substitute the AC voltage expression into this formula, we get current I equals Vm sin omega t divided by R, which simplifies to I equals M sin omega t, where M is the peak or maximum current, just like Vm is the peak voltage. One very important concept to understand in a pure resistive AC circuit is that the voltage and the current are in phase. This means that both reach their maximum and minimum values at exactly the same time. If you look at the wave diagram, both the voltage and the current follow the same sine wave pattern, rising and falling together. The phase difference between voltage and current, represented by the Greek letter phi, is 0 degrees. This in-phase behavior is unique to purely resistive circuits, where no energy is stored, unlike inductors or capacitors which store energy in magnetic or electric fields. The phasor diagram also shows this in-phase relationship. A phasor is a rotating arrow used to represent sinusoidal functions. Both the voltage phasor and the current phasor are pointing in the same direction at any given moment, meaning they rotate together and stay aligned, further proving they are in phase. This helps engineers visualize how current and voltage behave in the circuit at any point in time. Now, let's talk about the opposition to current flow. In a resistor, this opposition is called resistance and it remains constant regardless of the frequency of the AC source. The formula for this is very simple: resistance equals voltage divided by current, or R equals V over I. This means that for a given voltage, the current is entirely determined by the resistance, and there is no additional opposition like reactance or impedance that you would see in inductors or capacitors. So in a pure resistive AC circuit, energy is not stored, just dissipated as heat, and the current and voltage stay perfectly in sync throughout the entire AC cycle. This concept forms a basic but very important foundation for understanding more complex AC circuits, where other elements like inductors and capacitors come into play and introduce phase shifts and reactance. But in the case of a pure resistor, it's all about simplicity. Voltage and current rise and fall together with no delay between them.